Okay, good afternoon, everybody in the room and remotely connected. Thank you once again for being here. Today I have a problem, as you know. I need to stop lecturing at 4, and I apologize. I wanted to start at 2:30, but I am a bit late. We will get back this hour of lecture that we are losing today later on. I will tell you when. And please be aware that next Monday we don't have lectures, it's degree day. So the next lecture that you will have is Monday, March 28th, and Professor Navarra will talk. Professor Navarra was supposed to talk today, as you know, but I am replacing him. So he will talk on March 28th. Today, I am talking about climate and energy. You know that there is a strong connection between the two research subjects. And if you refer to the website, the web page of our course, the lecture is listed here. It's a new one. It's available from today. So I put it online at about 1 p.m., 1 hour ago. It's not yet on Virtuale, I apologize, and I will make it available in Virtuale later today when I will upload the video, maybe tomorrow morning. But it's already available here in my website. And this is the webpage lecture that I will follow as soon as it appears. This here by Professor Alberto Bellini, and he used the slides that are still available in Virtuale. Professor Bellini taught for about 6 hours. So given that I need to condense in 2-3 hours the lectures, I made a synthesis of what he talked about, but you can find the integral version of his slides in Virtuale. So if you are interested in expanding, for your knowledge, I let you know that actually what I removed were only case studies of individual countries. He looked into the energy budget of individual countries, in particular Italy. He devoted a significant part of his lectures to the analysis of the energy budget for Italy. I removed this part because I think it is easily accessible to you. It's very descriptive. And if you're interested, look at the slides by Professor Bellini. And as I said, the topic is extremely relevant to climate change because, as we will see, energy production is responsible for most of the human CO2 emissions. And therefore, it's clear that when we discuss about policies for mitigating climate change, we get involved into the discussion on how to accelerate the energy production through renewable energy, through renewable sources. In a way, sources that don't imply a significant release or a much lower release of CO2 emissions. It is also very relevant, this subject, because you know that energy policy is strictly related to development policies of individual countries and global development policy, which is in turn strictly related to the discussion on how to reach sustainable development. And therefore, this is something that actually would deserve probably many more hours of lectures. What I'm would like to provide to you with these 2-3 hours of lectures is just some body of facts related to our current energy budget at the local level and related to our current status in promoting the use of renewable sources, renewable energy. I'm not getting into policy and politics. I just want to give you information, background information that allows you to understand at what stage we are. First of all, let me start by introducing what is energy. And let me just try to expand this web page. And what is energy? It is, indeed, it is a good question. It is a good question because I quoted here in my pages statement by Professor Vincenzo Balzani. You may know this name. He is emeritus at the University of Bologna. He was candidate for the Nobel Prize. He's a chemist. And basically, he once said that if we want to, in a way, to puzzle somebody, we should ask what is energy. It is a difficult question to reply. Everybody of us has an intuition of what it is, but actually it's something that is hard to define. We have an intuition of what is mainly referred to electrical energy, but actually electrical energy is just a form of energy. Energy, I think we should refer to physics. It's mandatory for every process that involves movement of something, movement of bodies, and therefore it's very relevant to natural processes. It's very relevant also to development processes, to development policies. And energy appears in different forms. We may mention chemical energy, electromagnetic energy, electrical energy, thermal energy, mechanical energy, nuclear energy. We can convert energy between these forms with some implications that we will see today. And let me say that energy conversion is the only way to produce energy, actually. And during the conversion, as we will see, the quantity of energy is conserved while the quality of energy degrades. And in physics, it is defined energy has the quantitative property that must be transferred to a body or a physical system to perform work on the body or to heat it. And therefore, you can understand from the definition the fundamental role of energy in the Earth system and therefore our life. It's the ability to do work. So we require energy for any kind of work that we want to do, and physical work, whatever. And also our body requires energy for any kind of work, including thinking, including studying, whatever. So it's not only needed for, let's say, physically working, it's also needed for any of our activity. It is measured in joule, as you may know, but we are not really interested to the definition and the units. We are interested in the concept. Now, what is the role of energy actually for determining the human well-being? Let's also discuss in more detail this. You know, energy is related also to food production, is related to water movement, is related to, as I said, any kind also of intellectual activity. It's therefore essential to life. So, what is the source of energy over the Earth? It's the sun. It's the sole source of all energy in the Earth system, directly or indirectly. And you may think that this is strange, because you may think that, as we know, most of our energy today, most of the energy that we use comes from burning fossil fuels. And this is a problem, because it's generating a lot of CO2 emissions. And you may say, what is the role of sun in this? Actually, it is a fundamental role, because fossil fuels were generated by the degradation of organic matter a lot of time ago. And this organic matter grew up thanks to the energy that was given at that time by the sun. So fossil fuels are a form of fossil energy that was given by the sun to the Earth system maybe millions of years ago. And therefore you understand that this kind of energy, it's not renewable. Besides releasing a lot of CO2 emissions, it's a kind of heritage that we got from very past times that was like stored by the Earth system. And now in burning fossil fuels, we are exhausting this storage, this kind of reserve. So besides CO2 emissions, you understand that burning fossil fuels is unsustainable. And let's forget about climate change for a minute. Even if we were not concerned by the CO2 emissions, using as primary energy source, like we are doing now, fossil fuels, it's not sustainable. And this is a very good reason, another very good reason for finding alternatives. So the whole of the energy is given by the sun, for instance, through the photosynthesis, which allows vegetables and organisms that are capable of synthesizing through the solar radiation through photosynthesis to grow up. And it's in a way, the energy from the sun is in a way and definitely the only energy source that we can rely on. And you may think that you may be still concerned or a little bit doubtful on what I'm saying, because one may say, what about wind energy? What about, yeah, but wind energy is generated by the movement of masses of gases in the atmosphere, which means that, and this movement is originated by the climate cycle, and the power of the climate cycle is given again by the sun. Now, to emphasize the importance of energy, we may just mention, as you see here, example of energy consumptions for producing essential goods for the human life. So the production of 1 kilogram of meat on average requires 7 liters of oil. I am using oil now as a unit of measure for the energy. Okay, this is frequently used. When we want to measure energy, of course, it is measured in joule in the international system, but some technical systems use the equivalent volume of oil, because traditionally we produce energy by burning fossil fuels. So if we want to desalinate 1,000 liters of seawater, we need 3 liters of oil. Producing a ton of aluminium requires 5 tons of oil. And producing a car requires about 3 tons of oil. That is about 25% of the energy consumed by a car in its lifetime, etc. And energy production, as we will discuss more extensively later, accounts for about 75% of global greenhouse gas emissions by humans. That is mainly obtained with burning of fossil fuels. So 75% of our emissions are related to energy production. And you understand why the subject is then extremely related to climate change. Let me talk now about conversion. And let me be more clear in saying that we define today 6 forms of energy, which you can see in this table. The table is interesting in my view. This is by Professor Bellini, by the way, because it shows what is the process through which we can convert energy from one form to another. So the 6 forms are thermal, chemical, electrical, electromagnetic, kinetic, and nuclear. And if we want to convert the thermal energy in chemical energy, the conversion is through endothermic reactions. Or if we want to convert the thermal energy in electrical energy, the process is the thermoionic emission. If we want to convert electrical energy from the other sources, basically we can convert the kinetic energy in electrical energy, to give you an example, through electric generators. And this is what is done with hydropower production. We can perform all these conversions. All of these conversions can be performed by human. And as I said, the total energy is always conserved when transforming it. And this is the statement of the first principle of thermodynamics. The total energy of an isolated system remains constant. One thing that I need to tell you, this lecture is new, and therefore you will see some spelling errors. I already found a couple of them. And be patient, I will correct them. And if you have any, if you spot any mistake, or if you have any comment, please let me know. And keep in mind that I'm not an expert in energy production, and meaning that I don't make any research on energy production, renewable energy. Of course, I know these topics because they are strictly related to my teaching, and also to some extent they are connected to my research activity. But my research activity is related to water, not energy. Therefore, when I speak about water, I can speak with a good knowledge also of the latest research outcomes. When I speak about energy, the knowledge is more didactic, let me say this. I think this is important because, as I said, it's important for you to know what is the background of a professor and what is the type of information that you can obtain from a given professor. You already know that I am an engineer, and this is another important thing to consider. And therefore, being an engineer, of course, I have some connections with energy. I am an expert of hydropower generation. I made also research on hydropower generation, but this is a very small part, a very small subfield of energy production. If you talk to me, if you ask me, for instance, if I know the latest outcomes from research on solar energy, use of solar energy, or some of these processes of conversion, I would say no. I know what they are, but my experience is not that of a researcher in that field. And I think it is important because the aim actually of this subject of this course is to give you some science. And just to let you know, when Professor Navarra will speak, and Professor Navarra is a climatologist, so different background with respect to me. He's a climate modeler, specifically. So this is what he will tell you, but this is what I would like to anticipate to you, because again, it's important that you know what is the point of view, the background, the expertise of the teacher. Okay, so let me keep going. As I say, while energy is conserved in any transformation, however, conversion implies a degradation. What does it mean, degradation? Energy is conserved, but its capability to produce work is reduced. And in fact, the second law of thermodynamics deals with energy transformation and the natural tendency to move towards more degraded forms of energy, which cannot be used any longer. And what does it mean that the ability to do work is decreased? For instance, if you use electric energy to heat a body, this transformation implies that the energy is converted into heat, the electrical energy is converted into heat, and the capability to obtain work from heat is much reduced with respect to the capability of getting work from electrical energy. What is the reason why in our houses we bring electrical energy inside and not directly, I mean, other forms of energy? Because electrical energy has a high capability of producing work. And if we convert it, for instance, in heat, then it's more difficult. And, you know, you open the window and the heat goes out. So the total energy of the Earth system, which is our isolated system, remains the same. But you understand that while you can use direct electrical energy into your house to produce work, it's more difficult to use heat in the atmosphere. And therefore, let's be clear in saying that this is a natural tendency. There is a natural tendency of systems to decrease the capability of the energy contained into the system to produce work. It is the same like burning fossil fuels. You generate heat, and you may generate through heat electrical energy, but actually you decrease in this conversion, you lose some of the potential work. So you know that we say a consequence of what we said is that the total energy of the total capability of the work to be produced within the Earth system may look decreasing. Okay, because we have this Earth system that is, in a way, you may think it is isolated. It has an amount of energy, and the capability to produce work tends to reduce because there are energy transformation. Let me make another example. Think of energy, kinetic energy, or potential energy that is related to water. Water has a natural tendency to go down. If you don't limit this, water is a fluid, so it goes, it has a tendency to reach zones of lower elevation. And once that water flew down, you cannot use anymore the energy of the water to produce hydropower. And once that you used it to produce hydropower, you decrease the elevation of water, and then you get water into the ocean, and you can't generate any more hydropower by using the kinetic energy that is given by the gravity force. So your conclusion may be, how can we explain the fact that indeed water and hydropower is a renewable resource? It is very simple. Through evaporation, you bring back water from the ocean to the mountains, but evaporation uses energy which is given by the sun. So actually, I mean, this conversion back of energy to a form that is can be used to, again, to produce hydropower takes place because there is an increase of energy given by the sun. So the Earth system is not an isolated system. It is receiving energy from outside, from the sun. The universe is an isolated system. And in fact, we know that a consequence of the second law of thermodynamics is that the entropy of the universe is tending to a maximum, which means that there is a tendency of the universe to decrease its capability to produce work. And this is also an explanation of the fact that the life of the universe is not infinite. Now, in fact, fortunately, as it's written here, biological systems are open systems, which, thanks to the incoming of energy from outside, restore the positive global energetic balance. Let me, besides giving this classification of energy in 7 types, let me mention a second interesting classification. And I will also introduce a third one. A second interesting classification divides energy into 2 categories, primary and secondary energy. How are they defined? Primary energy consists of unconverted or original fuels. Secondary energy includes resources that have been converted or stored. So primary energy sources include fossil fuels, natural gas, coal, fossil fuel, biomass, flowing water, wind, and solar radiation. These are examples of primary energy. And those are the fuels that can be mined or extracted, harvested, and so they are primary energy. Secondary energy cannot be directly harvested. For instance, electricity is a good example of a secondary energy. Okay, we may say that you may say that electricity is also available in nature through thunders, but actually they are already the result of a transformation. So this distinction is important because, as I said, in any transformation, we have a degradation of energy. So it's important to be able to recognize what are the primary sources. Primary energy, and I am introducing the third classification. I think this is a motorbike, correct? Okay, so hopefully it will go. Primary energy can be distinguished into 2 categories, which are extremely relevant to our interest: renewable and non-renewable. I think the term explains the concept, and I'm sure that you know the concept, because if you are interested in climate change, you are also interested in renewable resources, for sure. And renewable means that these resources, these energy sources are replenished naturally, and this is important to say, on a human time scale, which means that we consider renewable something that can be replenished by, let's say, 100 years. So if something, in principle, you know, even fossil fuels can be reformed, can be replaced, can be replenished, but they take a lot of a time span that is much higher than the time span of a human life. Okay, so they are classified non-renewable. If you think of something instead that on the human time scale can be replaced, like, for instance, hydropower generation, water, along the human time scale, for sure, the water cycle completes several cycles. And typically, the storage in artificial reservoirs to generate hydropower, it's replenished within 1 year. Or if something really impactful or shocking happens, it may take some years, but still, I mean, the time scale is much lower than the human time scale. An interesting question is whether burning organic material is considered to be a renewable resource. And yes, it is considered, it may be considered also a renewable resource, because if you think about burning woods or burning organic material, some of these organic organisms, of course, have a time of substitution that is lower than the human lifespan. Still, this kind of energy production, this kind of energy forms are obtained through CO2 emissions at the expense of CO2 emissions. So I mean, don't assume that renewable sources are all emissions free. Some of them are renewable, but still imply the release of emissions. Furthermore, we will discuss also this later. If you think of hydropower, also hydropower generation implies some emissions of CO2, at least in during the construction phase, but also in the maintenance. The works that are needed to build the plants, to maintain the plants, imply some CO2 emissions. So actually, this is something that is relevant. Of course, the CO2 emissions related to hydropower are much, much lower of those related to burning fossil fuels. But actually, there is, and this is the concept that I would like to convey to you, in any form of energy production, there is an environmental impact, which has to be carefully considered. And it doesn't allow us to say that there is a real clean form of energy production. There are, of course, cleaner forms. From the point of view of the CO2 emissions, we can certainly identify a very well-defined divide between the sources, the energy production forms that are more demanding in terms of CO2 emissions, but actually, and this is something that has to be carefully evaluated by policymakers, we always have an environmental impact. On the other hand, we know that energy is strictly related to sustainable development, and we need also energy in order to sustain our development. But I mean, the trade-off has to be carefully evaluated. There are, of course, some very obvious statements, and burning fossil fuels is definitely something that we should leave in the future, we should abandon in the future for many reasons, and not only CO2 emissions, as I said, lack of sustainability, impact on the earth, etc. On the other hand, policies have to be carefully evaluated, and the scientific information, the scientific support is essential in this. Why it is essential? Because there is a progress that is really going very fast. There is really, things are really moving in energy production. So some forms that were considered not doable in the past now become feasible. And you can think of, for instance, solar energy, wind farms. I mean, today these plants have a very high efficiency. I can also mention small hydropower plants. Don't think at big dams. If you look at a river that is flowing, there is a massive amount of energy that is not used there. And now we have the technology that allows us also to take energy from flowing water. It doesn't mean that there is no environmental impact, but it means that it's really an innovation that may bring us to a completely different future within few years. I'm not talking about decades. I'm sure that in 5 years from now, we will have opportunities that we don't have now. And I can safely say this because if you look back 5 years, in 2017, I can tell you that the situation, the scenario was really different. And therefore, we can expect really something new in the future. And, you know, this is something that makes the life of a policymaker difficult. Because, of course, there is a very balanced interpretation that has to be taken on what is the most advisable strategy, to wait a little bit or just to try to force some changes by taking into account that any action that you take has implications and benefits, pros and cons. But I think that in this particular field, the role of science is really important because innovation is coming forward very quickly. Okay, and now, primary energy, you see here, this graph, I think it is nice, can be broadly classified into 3 parts, and which is that comes from crude oil, hard coal, natural gas, nuclear energy, etc. Another part is the energy that comes from wastes, unfortunately, burning wastes implies release of CO2 emissions, and also not only CO2 emissions, but also, there is an impact also on air quality. And then there is a third category that brings together wind energy, geothermal energy, biomass, hydroelectricity, wave and tidal energy, etc. And the secondary energy you can divide into electricity and heat, biofuels. Biofuels are also an interesting recent development, not really conclusive, meaning that, of course, biofuels probably may be more sustainable, not really sure, because they require a lot of water and they require also the use of a lot of land. And this is something that has to be considered very carefully, because some forms of energy production require a lot of land use. Think about wind farms, solar farms, and also biofuels. And biofuels do not resolve the problem of the CO2 emissions. I mean, okay, you resolve the problem of sustainability for some reasons, but they are not really the answer that we may expect. And then there is another form of secondary energy, which includes the petroleum products, manufactured solid, fuels and gases, etc. Okay. So let's talk now, let's go into more details and talk about the global energy budget and greenhouse gases emission. And here there is another spelling error, be patient because I will read everything. Now, here you see the numbers, and this graph is really informative. So the numbers are that basically, these are the percentages of global greenhouse gas emissions by sector. As I said, energy is about more than 70%. And then there is industrial processes, 5%. Waste, treating wastes, 3%. Agriculture, forestry, and land use, 18%. Of course, also agriculture implies release of CO2 emissions, but I mean, the figure here is quite clear. And also you see this graph. Of course, we don't go into the details now, but gives more details about the subdivision in subcategories. So if we talk about energy production, it is, as we said, 70%. And we have a percentage that is given by energy use on buildings. It's 17% of global CO2 emissions. And then we have transport, 16%, 17%. Energy use in industry, it's 24%. So, I mean, the industrial release of CO2 emissions includes not only those that are directly released, but includes also those that are related to the use of energy that has been generated by releasing CO2 emissions. And then you have the other details which give to you an overall picture of our status in terms of global greenhouse gas emissions. And when we say greenhouse gas emissions, it's not only CO2, but CO2 is the vast majority of it. Okay, there are also aerosols, etc., but CO2 is the vast majority. Okay, and now let's look at the primary energy use by fuel type. This is another interesting graph, which says that you see the percentages. So there are fossil fuels that cover the vast majority of, and this is a progress a long time. It was like that in the past, but basically the proportion is maintained up to today. And today, this graph was issued in 2007. And so from 2007 on, these are predictions. But you see that we can say, as we will see later, because we have other graphs, that the situation is basically unchanged. We have the nuclear energy, which is covering about 20% of the total energy production, and I will give more rigorous percentages later. And then we have the renewables. The renewables, it's another 20%, more or less. Currently, our renewable energy sources cover about the 20% of the global energy production, okay? And this rate has increased a lot in the past few years. And then we have the fossil fuels, natural gas, coal, and liquids, which cover most of it. Still cover most of it. You know that the natural gas is less impacting in terms of CO2 emissions, but still it's a fossil fuel. So, I mean, if one was could choose, of course, the natural gas is a most interesting option with respect to burning coal or other fossil fuels, but still it's not sustainable. And here you can see a more detailed representation of the world energy balance. And basically, fossil fuels is about, it's about 81%. And then we have coal, 27%, oil, 32%, gas, 22%. We have the renewable. Here, the renewable is placed at 14%. Actually, as I said before, this percentage is increasing. This graph was published in 2000. I think the data it's referred to the year 2016. So now from 14%, we already reached the 20%. And you see that hydropower is a very small percentage, is 2.5%, and nuclear is 5%. So this picture, I think it is informative, and let's look at the renewable energy. Wood is 5%. Wood, unfortunately, is still producing CO2 emissions. Biomass is 5%. Hydropower 2.5%. And then you have a lot of very small contributions. And according to this data, 2016, you see that the solar and wind summed together plus geothermal, they make a little bit more than 1%. It's not a big percentage. And now let me say a few words more about the hydropower, which I know quite well. Hydropower, and there is also discussion later on in this page. Hydropower is extremely important, not only because when we will see the statistics for electricity, actually hydropower is contributing 16% to global electricity production. So we are referring here to energy. This picture here refers to energy, not electricity. So when we turn to electricity, hydropower becomes more important. But hydropower is also important because it is flexible. If you compare hydropower with wind generation or solar generation, wind generation and solar generation, they are not flexible. You get energy when there is the sun, and you get energy when there is wind. Hydropower uses water that is typically stored in artificial reservoir, not all of it, but a significant part of it is using water stored in artificial reservoirs, and you can plan, you can schedule the release of water in order to compensate for the periods when other forms of energy production are less contributing. So hydropower is essential for the integration of several renewable energy sources. And even more important, hydropower can be stored. You know that energy cannot be stored, and for this reason, flexibility is a problem. Energy cannot be stored unless you accept to degrade a lot it, like with batteries. Storing energy in batteries, you know, implies a huge degradation and also an environmental impact. And we cannot think of storing a lot of energy into batteries. Hydropower is a means to store energy because you can store the energy into the reservoirs and you can pump it back. So it is easily renewable. And you may say, why should I pump it back? Because when I have energy, when I have energy available, I should use it. No, because for the lack of flexibility, you may have situation in which you have energy from solar power and energy from wind farms that exceeds our needs, our consumption, our requirements, our demands. And then you can use this energy to pump water back into the reservoirs. And it is very efficient. It is a very efficient process. Pumping back has an efficiency of about more than 80%. It's close to 90%. And this is, I mean, it's amazing. So hydropower has, as you see there, a small contribution apparently, but actually has a key role. Of course, hydropower is not evenly distributed. It's oddly distributed, like all the forms of energy production. Solar energy or wind energy, the distribution of the potential is odd, and also for hydropower. In Italy, we have a lot of hydropower. In Switzerland, they have more than what they need. But if you go into flat areas, of course, the potential is lower. Now, let's talk about this heterogeneous distribution. So half of the global energy is produced by China, the United States, the Arab state of the Persian Gulf. Half of global energy. And the Gulf state and Russia export most of their production. You know this. During these weeks, we know that Russia is exporting a lot of its energy production. And this is a problem. We know that it's a problem. We have the demonstration now that this is a problem. And actually, in peaceful times, we hardly would realize that this is a problem. Actually, I think that this is now proved to be a problem, which has, besides everything else, has an impact also on the success of climate change mitigation policies. Let's forget about the other things that perhaps are more important. I would say they are, because there is a war now that's ongoing, and there are also social disparities being originated by this war, also in other countries. So in Italy, we are already experiencing some induced social disparity by this conflict. And I mean, this is a problem. The fact that the production of energy is heavily distributed, it's oddly distributed, sorry, it's a problem. I would say that probably we wouldn't have this war if Russia had less energy to sell, because you can understand the motivation. This is something that Russia can use to support their intent, the fact that they have energy. Now the question is, how long can Europe resist? Interesting question. And it is not easy. I mean, it is not easy to discuss a so topical issue these days, but on the other hand, I thought that if one has to talk about energy and climate change now, one cannot ignore what's going on. And I had the same feeling during the pandemics. The pandemics, I think, had a relevant implication on climate change mitigation policies for several reasons. And it may look like it is a lower priority problem. Maybe it is, but I think it is something that we have to talk of, especially in an academic environment. Not to speak about, not to speak of all the other implications, but it's not here the right place where to discuss the other implications. For energy, I think it is an important implication. Okay, and yes, please.
I'm sorry, I think there is a mistake there when it says that half of global energy is produced by China, United States, Arab states, but it doesn't mention Russia, and then it says that China hasn't enough energy. I didn't understand.
Sorry, I mean half. It doesn't mention the other states because it says that half of the global energy is produced by China, the United States, and the States.
But then I didn't understand why it says that China hasn't enough energy.
Because China is producing a lot of energy, but it's not enough to satisfy their internal demands. Because okay, this is what I meant to write here.
Yes, I thought it was a mistake.
Yeah, okay, that's fine.
Thank you.
Okay, and now let's also provide some statistics on the global energy use now, not production but use. And for the residential use, we have 21% of incidence. Transport is 29%. Industry is 29, and other is 21. Again, this is use. And this picture here, which I could also expand, just 1 second, shows the global energy consumption from 2000 to 2020. I think this is a figure from Wikipedia. I think this is consumption, not production. And I think it is interesting to notice the trends, okay? And in particular, with the curly brackets, you see some statistics on the last 6 years, I would say. Yes, it's 6. So for the use of coal to cover the energy consumption is increased a lot from 2000, but in the past 6 years we had a decrease for use of coal. The use of oil, we had a decrease last year, but last year the decrease was for the pandemics. So I don't think it is really significant. For coal is more significant because you see that the trend is extended over the 6 years. And I would say that for coal, during the past 10 years, we can say there was a decrease. Natural gas, there has been an increase. And there has been an increase which is motivated by, is compensated, the increase of the natural gas compensated a little bit the decrease on the use of coal. And then there is the nuclear, which is more or less constant with a small decrease, and this is also due to concerns that were related to the use of nuclear energy. We have an increase of the hydro. The increase of the hydro is mainly motivated by small plants. There is also the incidence of some new dams, but it is also motivated by the progresses, the technological progresses that I mentioned before. And then there is the other renewables, which you see there is a significant increase, but is still a reduced percentage, but the increase is really significant. The question with the other renewables is what is the potential for the future? So we had a strong increase in the past 10 years because there was indeed, some financing, some support that supported building wind farms, building solar farms, but there was also a land occupation generated by these additional renewables. And the question is whether we can really push forward this strategy in a significant way. For instance, in Italy, you see that, you know that it's a problem, meaning that now we use the space offered by roofs, by buildings, which is fine. But if you start occupying the land, then there is an impact, an environmental impact, and also you subtract land to food production, which is, so it is prompting some concerns about sustainability. Now, this figure shows the total energy consumption by source. It is more or less referred to the year 2010. It is basically giving the same information. and that we know from the past graphs, because we knew that fossil fuels in terms of energy production cover the 80%, and it is mirrored here, the same information in the energy use. Now, energy consumption, let's talk about the energy consumption per person, which is another important indicator on the heterogeneity of energy consumption. In North America is very high, while of course, in developing countries, it's low and more renewable. This is interesting. This is interesting. In developing countries, of course, you can understand why. They rely more on renewable resources. And this is, anyway, I think it is interesting, which means that in those countries where the development was more intensive, this development was also more unsustainable, okay? Because of course, if renewable resources can cover only a limited part of our needs, it means that basic needs could be eventually covered, but more intensive needs, more, let's say, needs of more developed countries cannot be covered. And this may be an indicator that our development model needs to be revised, of course. Of course. There was a significant decline in energy usage worldwide caused by COVID-19, okay. Notably in the iron and steel industry, because there was a decrease in demand. And it is interesting to observe that to reach levels similar to that in 2019, and there would need to be an increase in the global demand for manufactured goods by the iron and steel industry, that it's not so, I mean, it's not so likely. So basically, maybe that COVID-19 in this sense helped a bit, because it caused an economic impact, it caused an impact on the economy, and it caused also a crisis, as we know. And this crisis probably it's an opportunity to decrease our global energy demand. Let also me point out that, as you may know, crises are anyway an opportunity to revise a development model. Very often, if you look at history, development models were revised after a crisis. And this is not meaning that we should, I mean, that crises are beneficial. Crises are for sure, at least for the people that live during them, have a negative impact, but the ability, our ability is, as we said repeatedly during the COVID-19, to transform crises into opportunities. And COVID-19, I think, gave several opportunities, including maybe the opportunity to revise, to rethink a little bit our development model. Also, you know, to revise a development model, you need an international cooperation. And I think COVID-19 a little bit stimulated it. I'm not saying that I was completely happy. I think we could have done more, but still COVID-19 stimulated, at least at the European level, I think, some cohesion. And the same can be said for the current economy. I mean, all these policies, PNRR, so emergency plan for recovery, I think these are opportunities. There is an high risk to lose these opportunities. So if you think at the funding for recovery, I mean, it is extremely interesting. There is conversely an high risk to lose the opportunity in several sectors, including development models, energy production. I'm not giving answers to you. It's not my role. Okay, the role of the science is to give facts, to provide knowledge, and I'm not giving answers. So because one may wonder, what could we do in order to transform crisis into an opportunity? I think science can give some knowledge, but taking a decision is It's not the role of science, it's the role of politics. Politics in a positive meaning. I mean, I'm not saying politics to mean something negative. Politics means taking decisions in a democratic manner and taking decisions for reaching a target, a common target, and a joint target for beneficial development. Let's talk a little bit more about renewable, because there is an important question here. Can we hope in a future where all the energy demands will be covered by renewable in the sense that we mean today? Okay, so actually, today we are not including nuclear into renewable. Maybe in the future that we have more opportunities for producing nuclear energy in a more safe way that makes may make nuclear energy also very close to a renewable source. And this may come quite soon. You know that there are several researches now on nuclear fission, but if we forget about nuclear energy, what is the real potential that we may have? Okay, now, you know already some of the statistics, and let's look at this graph. So first of all, I already mentioned to you, now we are at 20% of humans' global energy consumption covered by renewable, including almost 30% of electricity. So if we talk about electricity, we are close to 30%. This is the statistic is not the same for every country, but most countries are expanding their sources. And then let's look here. You see that this is from 2011 to 2020. And for the past 2 years, there is a detail in the contribution of this graph is reporting the progress of renewable energy production. And in the past 2 years, it is reporting the details. So it's wind in green, solar energy in yellow, and hydro in blue, and other in gray. First of all, note that in the past year, there has been a significant increase. The trend is not linear here. The trend is exponential. And the expansion was given, most of it, by the wind. And solar, it's already quite close to a stable situation. It's still increasing, but not as much as the wind. There are pros and cons. Also, hydro is increased. And hydro is increased, as I said, for the contribution of some new huge dams and the contribution of micro generation. What are the pros and cons of these? I already mentioned a little bit. Wind. The problem is noise and visual impact. Occupation of land, 3. Land occupation is not so relevant. I mean, below, in the soil covered by wind farms, we can use it for agricultural purposes, for producing foods. And also keep into account that some of the wind energy is produced in the open ocean. So for instance, the platform that were used originally for extracting oil from the sea bottom now are reconverted to wind farms or wave energy farms. So occupation of land is not really an issue, but the visual impact and the noise, they are, especially the noise. I would say that it's really something that is a bit disturbing. Solar energy, the problem is the occupation of land. And of course, even for solar energy, there are now new projects coming on and of solar farms floating over the sea surface, which is okay. It is, of course, posing some technological challenges, but still it's okay. But most of them are occupying land, and the land occupied by solar farms, it's indeed land that you cannot reuse. And there is also an impact on the water cycle because infiltration is reduced. And also there is an impact on flood formation because what was before the installation of the solar farm, what was an open field now becomes a field where rainfall is concentrated in few points. And being concentrated, you have less infiltration and more production of river flow, which may cause floods. So there are studies ongoing on this. Hydropower, we will talk in a minute about the problems more extensively, so let's postpone it. I move to the next figure, which is years data from the year 2012, which is the total energy production by countries, which confirms that there is an heterogeneous distribution. What is also interesting to see here is the trend. There is a positive trend for all countries, but some of them are more, the colors are explained in the legend here. Some of them are increasing more significantly. Now, first of all, let's note that we have two vertical axes here with a different unit, or same unit, different scale, to be more rigorous. And in particular, there is the left axis, which is for the red line, which refers to the total global energy production. The red line is total world. While the right vertical axis is the scale for individual countries. Yellow is China, brown is Russia, brown is this one. Light blue is Africa, blue is United States, green is Europe, dark green is Central and South America. Again, this gives to you an overview of the distribution of energy production and the trends. The trend of China is impressive, but we know this. We know that China underwent a significant industrial revolution, which implies an increase of demand of energy and therefore an increase of production. Still, China is importing. Same statistics as before. This refers not really the same because it refers to electric energy. And this is for the year 2018. And if we consider the renewable electricity, 45% of it is generated by hydropower. I said that about 17–20% of electricity is generated, total electricity is generated by hydropower. If we look at the renewable, the hydropower becomes 45%. Nuclear here is considered renewable. And, you know, there are some different classifications, but I would say that it's renewable in a way that it doesn't, the fuel doesn't get exhausted for nuclear production, energy production. Wind is 13%, solar 6%, biofuels 5%, other 3%. Now let's talk a little bit about hydropower. We already mentioned that it's flexible and it can allow to pump back water into the reservoirs. And now I wanted to talk about the implications, not positive implications of hydropower. First, let me say that recently there have been at the global level an increase of hydropower generation. We know this because we already gave the data. And this increase is also motivated by the construction of new dams, new large dams. And this is a picture of the Three Gorges Dam in China. It's an important dam. It is a project that it's in my opinion, is very appropriate because China is increasing energy demand, and I think trying to meet these demands through hydropower production is something that I approve. On the other hand, there is to say that the size of a dam is directly proportional to its environmental impact, and this is really huge. It's not the largest in the world, but actually recently several large dams were built in several countries. Another dam that I think it is interesting that you know the story. Here you have the link of the Three Gorges Dam in Wikipedia. I suggest that you take a look because it is very interesting. Just 1 second that I try to. I already donated to Wikipedia, so okay. And just have a look because it's interesting. Here, if you look at the volume of water, it's about 27 millions of cubic meters. Oh, dam volume, sorry, because the volume of water is much more. It's the total capacity is 40 cubic kilometers, which I mean, it's a huge dam. Another interesting one is not linked, but you can find it in Wikipedia. It's the Millennium Dam in Ethiopia. It's under construction. It is being filled now. Let me see, I think there is a picture. And yeah, this is a satellite image of the reservoir in 2020. And I think they started filling it up in 2015, I think. I had the opportunity to be involved in some technical design related to it, just hydrological. And I tell you, it's extremely interesting, but this is a controversial project because, when you build a dam on a river, you have an impact on the downstream river flow. And when a river is so important, like the Nile River, which is feeding not only Ethiopia, but Sudan, Egypt, the most important ones, of course, you are not really deprivating the downstream river flow, but you are impacting it. And downstream, there are other dams. And also keep in mind that a dam causes an increase of evaporation. An increase of evaporation means that there is a water shortage, an additional water shortage. Okay, and another interesting thing in Wikipedia is the list of the largest dams. Let me see if I can find it. List of largest dams, and this is interesting because you can see here, I think they are ordered there for reservoir. It's not ordered for reservoir volume, but you can order it. I don't think the Swan Dam is reservoir volume. Yeah, okay, anyway, this is a list. I'm still not sure this is the list I was looking for, but anyway, if you look at on the web and get information on the largest dam, it's interesting. Why it is interesting? Because among the several impacts that a dam may have, there are some of them that are not so obvious. So there are some obvious impacts, like increased evaporation, and the impact on the water cycle, downstream river flow, and downstream groundwater storage, because building a dam means that you keep the water upstream, and therefore downstream you have less water, which means less groundwater because there is less recharge. But these are quite obvious. But actually, there is also an implication, because by concentrating huge masses of water in one specific place, and here we are talking of really large volumes, there is the feeling that we are modifying the gravitational force, and there might be also an implication on the climate. Why? At the local level, for sure, you understand. At the local level, these are big lakes. but also at the global level, there might be an implication because there might be a small change in the inclination of the terrestrial axis, which means significant changes in climate. Some of the past climate changes, natural climate changes, are explained. There are some theory that explain them with changes in the inclination of the terrestrial axis, which means a lot in terms of climate change. So the question is the construction of a huge dam in a specific place capable of modifying perhaps the inclination of the terrestrial axis, the shape of the Earth, and therefore inducing a global climate change? For sure, it's not an easy answer. Some scientists think that this is unlikely, because even if we are talking about huge masses of water, it's something that some scientists say it's negligible with respect to the total mass of the Earth. Other scientists say that we are getting into something that we don't really know. And we have a limited knowledge of it. It's like climate. It's something that we have a limited knowledge of it. And therefore, this kind of intervention, may have this kind of impacts that could be not so easy to revert. This is not to say that these dams shouldn't be built. Dams, hydropower, as I said, it's an essential resource. I just want to give you the idea that the problem is really complex. It's really, something that it's complex, and therefore there is no easy answer to it. There is no easy answer. You need science, you need knowledge, and you need ideas and rigor. Okay. Let's talk about wind energy production. And this graph from Wikipedia again gives the progress of wind generation. We already know that it increased a lot recently. Here you see the contribution of each country. And you see that indeed there is a significant increase in Asia, also in Europe. The trend is a little bit flatter, but there is some increase in Europe. And this is the distribution of the wind power density potential. Why it's important to analyze the distribution, the spatial distribution of this energy potential? Because for the same reason why we discussed the problems that are originated by an odd distribution of energy production. And if we are interested in promoting a new development model, there is only one way through which it can be reached, through equality, diversity, and inclusivity. So if we promote a new model, the new model will be successful only if it is equitable. This is why there are some important declarations related to sustainable development that mention equity, because we understood an important thing, that these new development models cannot be imposed with the force, cannot be imposed by the top. They have to be promoted by the bottom. They have to be promoted by people. And what is the reason why people, the global community, may be interested in promoting something if they see that it's beneficial in a equitable way? And therefore, it's important to study this distribution of energy potential, because if we want something to be sustainable, it must be equitable. There is the Declaration of Dublin on Water Resources Management, which emphasizes in one article the role of women. And one may say, why they did mention the role of women? Because they recognize that there was a gender disparity in policy making, in politics, in whatever. And they understood that this disparity was an obstacle to promoting a new model. A new model, again, should pass through equity, diversity, and inclusivity in a real factual way, not just by lip service, because you know that when we talk about new development models, when we talk about climate change, sometimes we pay lip service. Greta Thunberg said blah, blah, blah. I think she exaggerated a little bit, but the message is clear. The message is clear. So let's be in favor of equity, diversity, and inclusivity in a real way, which means that we have to accept to step back in something of the benefits that we are used to take advantage from, which is not easy, of course, but I think, okay. And the global distribution of solar irradiation, same thing. This is an important premise. I want to conclude this lecture by mentioning the water, food, energy nexus. Because when we talk about energy production, we already mentioned that we can't avoid to talk about other social policies. We mentioned politics, international relationship, and we mentioned already irrigation and land grabbing. Land grabbing in order to produce energy means that we cannot use the land for producing food. Indeed, water, food, and energy are intimately related. And this is why the FAO promoted recently the concept of an integrated approach to water, energy, and food management, which is, I mean, you may say this is trivial because we already discussed that energy is related to water, hydropower generation, etc. We discussed that energy is related to food because agriculture needs energy. And also, it's quite clear that water is related to food, and therefore that there is an intimate connection. And but again, this has to be recognized. And you see that this concept puts the stakeholder dialogue at the center, because again, equity, diversity, and inclusivity, not top down, but bottom up. And this is something that I'm just mentioning here because, sorry, this is something that shouldn't be here. I see now, but I wanted to put this mention to the water, food, energy nexus because it's another essential concept that I would like that it's part of your background. Okay, so again, I apologize because now I have to rush, and I just would have time for a very quick question if you have any. So I'm wondering whether. Okay, so let me close the registration. And